Good morning, good afternoon, and good evening, everyone, from wherever you're joining us, and welcome to today's webinar, Survival Analysis for Immature Data, a review of techniques and lessons learned. Today, speakers will present the techniques of survival analysis, their application in economic evaluations, and lessons learned from conducting survival analysis on immature data, addressing the challenges of analyzing different outcomes. I'm Sydney Otamanchuk from the events team at Scientist.com, and I'm happy to be your host for today. I'd like to thank the sponsor of today's event, Icon, for making it all possible. I now want to take this moment to introduce our speakers for today's session. We have Tim Baker and Manikanta Dasari joining us today, both of whom are lead consultants within health economics and epidemiology at Icon. Tim brings forward experience in economic model design and implementation in multiple disease areas, having supported HTA submissions in more than a dozen countries. Manikanta specializes in developing early economic models, global submission models, as well as supporting country-specific HTA submissions. I'm thrilled to have these two speaking with us today. And now, without any further delay, I'm pleased to welcome Manikanta to join me. Okay, take it away whenever you're ready.
Thank you, Sydney. Thank you very much. Thank you, everyone. Thank you for attending the webinar today. So for our discussion today, we'll start with an introduction to the fundamental concepts of the survival analysis, including survival and hazard function. And then we will review various types of survival analysis methods, along with a brief discussion on advanced survival analysis methods. Then my colleague Tim will be presenting a couple of case studies where we projected the long-term survival from the immature data. So as you may know, the survival analysis is also known as time to event analysis, which used to analyze and model the data where the outcome of interest is time until a particular event occurs. It measures the time between the exposure and occurrence of the defined event, and exposure can be diagnosis of cancer, where the event could be death. And it is not only limited to the oncology. Some other examples include the time to liver cirrhosis from the hepatitis diagnosis, and some other examples like time to treatment discontinuation from the initiation of the treatment or randomization to the treatment. And these survival techniques are not only help to determine the time to event or characterizing the event rates for the duration of the clinical trial, but it also allows extrapolate the event rate over lifetime horizon, which is needed for the health economic evaluation. So in the further slides, we will be discussing more details about the survival function and why we need to do these survival extrapolations. In this slide, we'll be discussing why the extrapolation of the survival data is important, especially for the cost effectiveness models. As you know, the cost effectiveness models often require the estimates of time to event data to accurately predict the costs and health benefits over a long time period, as recommended by the HTA guidelines. However, the clinical trials usually conducted over a short time duration due to the high cost involved and the ethical considerations. So this leads to a gap in the data. And so for this reason, we need to perform the survival extrapolation. So this is an so here in this figure you can see that we have fitted some of the survival extrapolations to see the how the survival is trending over the long time horizon by using an observed data of only 48 months. So in this slide we will be discussing the survival function. The survival function presents the probability of survival beyond a specific time point, or the probability of not experiencing an event of interest. In this example, you can see that 70% of the patients are still surviving after year one, which means 70% of the patients did not experience the event of interest, which is death in this context, after 12 months. In this slide, we will be discussing the hazard function in comparison to the survival function. As mentioned in the last slide, the survival function focus on the probability of not experiencing the event of interest, while the hazard function focuses on the occurrence of event. The hazard at any point describes that the instant risk of the event occurring, assuming the patient is still surviving until that point of time. And essentially, it reflects how quickly individuals are experiencing the event. For example, the rate at which the patients are dying, the rate at which the patients are discontinuing the treatment. A high hazard indicates a steeper decline in the survival curve, whereas a low hazard results in a more gradual decline. So it's important to remind that survival probability lies in between 0 to 1, whereas hazard represent a rate, not a probability. So it can exceed 1 as well, but they cannot go into negative because survival function is not going to increase over the time. So, these are the major types of the survival models. So, we'll be comparing those survival models in this slide. So, first one is non-parametric model, which do not assume any specific form of the distribution for the survival times, and they are quite flexible and can adapt to the data without requiring any predefined assumptions. So, one good example of the non-parametric method is Kaplan-Meier estimator, which is very common example, which provides a survival curve based on the observed data without fitting any particular distribution or any particular model. And the second model type is semi-parametric model, which combines the features of non-parametric and parametric approaches. They do not require any specific distribution for the baseline hazard, whereas it allows the influence of covariates on the hazard. So, and the final type and most common type of the model is parametric model, which assume a specific distribution for the survival times, and they involve fitting a model to the data based on the predefined statistical distribution, such as exponential, variable, log normal distribution. So these models can be these models can provide precise estimates when the fitted data is matching with the observed data. So each type of model has its own strengths and weakness, and it can be chosen based on the nature of the data. So we'll be discussing more about these models in the further slides. So before going into the specific type of models, so maybe it's good to learn about the censoring, so which occurs when we don't know the exact time of an event for especially some individuals in the trial. So there are three type of censoring: left censoring, right censoring, and interval censoring. So in this example you can see 5 patients. So for the patient number 1, we have all the information and the event occurred before the end of study, so that's why it's not censored. Whereas the example number 2 and 3 represent a case of right censoring, where we don't know when the event of interest happened. Patient number 4, for patient number 4, though the event occurred before the end of study, but when it started, we don't know when it started. So this case is known as left censoring. And patient number 5 represent a case of interval censoring. So though the event occurred but in a specific range of time, but we don't know the exact moment of time when the event occurred. So these are the different type of censoring. So as discussed previously, so the Kaplan-Meier estimator is a good common example of the non-parametric method, which provides a survival curve based on the observed data without fitting any predefined model or distribution. So Kaplan-Meier plot represents the survival probability at a given point of time. In this example, you can see that 70% of the patients did not experience the event at month 12. And other statistics includes median survival, where the survival probability is equal to zero 0.5. And the vertical lines in this Kaplan-Meier plot represent an occurrence of event, whereas the horizontal line represent the duration during which there is no event occurred, and the cross on the horizontal line represent a censoring event. So this is a simpler representation of the Kaplan-Meier curves. And as I mentioned previously, Kaplan-Meier curve provides the analysis based on a single factor and observed data, and it doesn't consider the impact of multiple factor or multiple covariates which has impact on the survival, such as age, gender, response to the treatment. So but adjusting for these covariates impact on the hazard is really important while exploring the survival. So this involve using a regression type of models, and a good example of this regression type of model is Cox proportional hazard model. So the key assumption of the Cox model is that hazard ratios do not cross over the time and parallel over the time. So this assumption is also known as proportional hazard assumption. So it can be tested by using various tests like visual inspection of the lag cumulative hazard plots, and by conducting Schoenfeld residual test. And after by looking at the results of pH assumption test, if the pH assumption proportional hazard assumption is violated, so it's recommended that fitting two independent survival model, and when the pH assumption is not violated and valid, fitting a single independent model where the treatment is an adjustment factor is recommended. And the next and most common type of model is parametric model. So there are two type of models under parametric model. One is proportional hazard model, and the second one is accelerated failure time models. So proportional hazard models examines how different covariates such as age, treatment affect the hazard ratio or hazard rate or risk of event occurring, whereas accelerated failure time models focus on how covariates influence the time until an event occurs. So instead of modeling the hazard, accelerated failure time models estimates how effect of the covariates accelerates or decelerates the time to event. So in this figure, you can see that hazard ratio is the vertical distance between the survival curves, that is the treatment effect applied to the hazard ratio, whereas the accelerated failure time measures the time ratio represented by horizontal distance between the horizontal distance within the survival curves, where the treatment effect impacts the time to event. And the most commonly used parametric distributions are exponential, Gompertz, Bible, log logistic, log normal, gamma, and generalized gamma. So here is the criteria for choosing the modeling approach. So based on the results of proportional hazard test, so if the plots are parallel and do not cross over the time, so we will be so it's recommended that fitting a single dependent model by using treatment as an adjustment factor. If the plots are not parallel and crossing over the time, fitting two independent models is recommended. However, when the hazard plot is complex and not the straight line, so we may need to consider advanced methods such as piecewise extrapolations or response-based landmark models or mixture cure models. So in this session, we will be briefing about three advanced parametric model which are mostly used in the handling the immature data. So first one is piecewise modeling, second one is response based landmark analysis, and the final one that we will be discussing is mixture cure modeling. So coming to the piecewise models, so piecewise models are useful when fitting the complex survival functions by breaking them into various intervals, and we are calling these intervals as pieces in the current context, and each piece will be fitted by a separate model. So these model can be a parametric model, semi-parametric model, and non-parametric models. So for example, in this survey plot, you can see a distinct trend in each and every piece. In the first one, the hazard rate is gradually increasing. That's why a survival is decreasing slowly. Whereas in the segment number 2, you can see there is steep increase in the hazard. That's why you can see steep decrease in the survival. Whereas the segment number 3 and final segment represent a decrease in the hazard. That's why we can see a plateau in the survival. So by considering the distinct nature of the hazard across the time periods, fitting piecewise models is a good option. However, the main challenge would be determining these cutoff points or intervals. And another thing is that we need to have the sufficient data to fit the separate models for each and every piece. So that's the main challenge. So having sufficient data and determining these cutoff points or pieces is a challenging thing. The next type of advanced model or flexible model is response-based landmark model. So before going into this model in detail, maybe it's better to understand the concept of heterogeneity, uh, which help us in making good and accurate interpretation of the survival predictions. So majorly there are two types of heterogeneity. One is explicit and the second one is latent. In the explicit heterogeneity, that's nothing but a observable difference between the individuals, which is measured and known in the trial, such as age, gender, and response to the treatment. Whereas the second one, unknown heterogeneity or latent heterogeneity. So the heterogeneity is due to unobserved or hidden factors. So in these slides, we will be discussing the method where we can extrapolate the survival data with explicit or known heterogeneity. So considering heterogeneity while extrapolating the survival enhance the accuracy of predictions. In this predictions in this example, we have observed that the survival data is impacted by the response to the treatment, and you can see that the survival of the responders is higher than the non-responders. Fitting separate models to these two subgroups will help us in making the accurate predictions or accurate projections. And at the same time, to avoid the underlying bias, fitting the separate models from the response assessment point is recommended, because as we know, the response assessment in the trials usually performed after a certain point of time from the initiation of the trial. So in this approach, the here we can see that the survival extrapolations are performed from the landmark period, which is also known as response assessment period in this context. And the overall survival for the through this method can be calculated by weighing the survival function for each response group according to the proportion of patients at the response assessment point. The next and the final flexible model that we will be discussing is mixture cure model. So as discussed previously, there are two type of heterogeneity in a population. When heterogeneity is known and measured in the trial, we can consider models such as response based landmark models. Whereas when the heterogeneity is not known and it is not observed in the trial, so considering mixture cure models is recommended. Mixture cure models assume that a population consists of two or more different subgroups, and in this example you can see that the survival is no longer is declining to the zero, and after some point of time the hazard is equals to the hazard of the general population. So that means the population considered contains more than one subgroup, and a subgroup's survival is equal to that of general population. So that subgroup where the survival is equal to general population can be called as cure fraction or cure subgroup, and other subgroup is called as non-cure subgroup. So when we have two different subgroups, so we can consider this mixture cure model. So in this figure you can see a clear depiction. So here is the survival projection when using the standard methods, whereas fitting two different models for cured and non-cured fractions provides a different projection. And similar to the response based landmark models, the overall survival of the population can be calculated by weighing the survival function of the cure fraction and non-cure fraction. So this is about the mixture cure model. And here is the criteria when choosing the different models or distribution. So when we have the complete data from the trial, so then we all need to concern about its fit to the observed data, and which can be evaluated or measured through the visual inspection statistics such as AAC and BAC. Whereas when we have incomplete data, and when we are fitting the various distribution, we need to compare the observed data with fitted projection, along with checking for the clinical plausibility and considering statistics such as AAC and BAC. So this is the hierarchy for choosing between the models according to the nice DSU. Uh, as the next step, my colleague Tim will be presenting couple of case studies where we have projected the long-term survival based on the immature trial data. Tim, over to you.
Yeah, thank you, Manny. Thank you for that overview. As Manny stated, the goal today, at least from the case study perspective, is to illustrate a few of the concepts that Manny covered for us. We're going to start in the next slide with our first case study demonstrating the landmark approach in one of our previous projects. So essentially, the situation in this case was a sponsor came to us with some early phase data, or some early data released from their phase 3 clinical trial, but it was limited in the outcomes it covered. It presented progression-free survival, but not overall survival. It also highlighted the best objective response categories for patients included in the trial. So based on these limited outcomes, there were some strategic questions around what the data tells the investigators in terms of expectations for their new product, what sort of context clues do we have from earlier phase studies that are relevant based on these phase 3 outcomes, and how do we synthesize this data? How do we start to make decisions about positioning for a global launch strategy, considering other evidence synthesis projects, considering other gap closing studies? Essentially, what can we do with this early phase data while we wait for the remaining phase 3 trial outcomes to come in? The goal, as I said, was mostly around preparing for some of these strategic questions, preparing for HTA and regulatory submissions across multiple countries based on this early phase 3 data, as well as being prepared for when some of the later data analyses were available out of this phase 3 study, as well as how do we emphasize these phase 3 results in the context of our earlier phase data. And the challenge in this case was to develop a statistical, or a survival model, I should say, that supported development of economic analyses, developed or supported some of the strategic decision-making about product positioning, and about a very important strategic comparison against other competing therapies that were also on the pathway to launch and submission and regulatory approval. So the question is, how did we do that? And how did we understand and quantify the uncertainty coming from some of these early survival models and some of this early data, and what risks are associated with that uncertainty? So how we ended up approaching this was to leverage what Manny described as the landmark survival approach. Essentially, what we did was to try and synthesize the evidence from early phase studies, so 1B and 2 phase studies with longer follow-up, and place them in the context of the phase 3 trial results, relying on the best objective response classifications as our stratifying factor. So this landmark approach essentially said, well, we have from one source our expected follow-up, so in the graph in the middle, our expected survival projections over a longer observed period for each of our response categories. So complete or partial response, stable disease, and progressive disease. So in order to construct an overall survival curve to match the phase 3 data progression-free survival, we use those response categories at a 6-month landmark to weight together the overall survival projections developed from the early phase parametric analyses. So in the center, again, you can sort of see those component pieces for complete or partial response, stable disease, and progressive disease. And on the right, you can see the historic progression-free, that's the green line, and overall survival, the light blue line. So that's the data informing our parametric analyses prior to weighting. And you can see the gold line, the progression-free survival from the phase 3 data release, and the red line. Now, I said before that the overall survival data were not released in this first data cut. What we were able to do is, through continuing to work with our sponsor, we were able to look at a later release of data and cut the time down to what would have been available in those first 18 months. So we were able to reconstruct what the Kaplan-Meier curve would have looked like had we unblinded the data. And you can see the fairly enticing distinction between the red line and the blue line. So historic performance for overall survival from earlier phase studies, and the red line, phase 3 performance. Looks like a really important to measure, important to include, and important to consider advantage. But we can also see that there is a little more than 70% of the trial population that does not record an observed OS, overall survival outcome, at 18 months. So this is what we would consider very immature data. Median survival has not been reached. In fact, we've barely reached the first quartile. So the outcome of this essentially involved a lot of different steps in demonstrating this approach, first with our sponsor, and secondly with the target audience, in terms of engaging the early scientific advice process for a couple of HTA authorities around the world, and being prepared for what comes next, being prepared for the next data release from the trial, and developing our analyses in a way that leveraged a modular construction so that we could always be prepared for the next set of data to be released, and we could easily update all of our projections to leverage those new outcomes. And essentially, the takeaway here is that our landmark survival approach worked fairly well for the first evaluations of the sponsor's product. It carried through a lot of their internal strategic decision-making. And as time went by and we were able to update the data analysis with future data cuts, it became more and more clear that some of the findings that we generated in our early outcomes were realistically well supported by the phase 3 trial data. But ostensibly, some of our cautions and some of our uncertainties were also still persistent, as the second and even the third data cut still made it difficult to analyze overall survival data, as in the second case, median survival had not yet been reached. And then in the third case, it had just been reached when the data set closed. And I should say, all of these graphs that I presented here and the fundamental elements of this analysis were first presented, I would say, actually, I can tell you exactly, it was in 2015 at the EADO conference in Marseille, France. And we'll provide a reference list when we get to the end of this presentation section, along with a series of other publications and presentations derived from this analysis, highlighting the sort of responsiveness of this modeling technique and this approach to modular design that allowed us to keep pace with future data releases out of this study. That having been said, we're going to transition now into the second case study and talk a little bit about how we evaluate some of these comparisons. So when I said that the landmark survival approach was received fairly well as an early assessment, it rapidly became clear that the gold standard in health economic assessment for oncology indications is realistic overall survival data, not just from the primary intervention trial, but also a synthesis of data for all the competing treatments. So in the second case study, we'll talk a little bit about other methods that we tested for early assessments of overall survival and early comparisons, and part of that strategic decision making, and the opportunity that we had, again, to follow on trial evolution to do a comparison of some of those early methods to the observed data. So both of these case studies are in a disease area of metastatic melanoma. It's a solid tumor indication with, at this point, a fairly crowded list of competing therapies, with a number of targeted therapies, multiple combination regimens, in addition to immunotherapies, both in monotherapy and combinations. And this is another example of a product being introduced in combination therapy with an existing monotherapy. And the sponsor had questions about what early results from the phase 3 study indicated for potential future opportunity in comparison to the existing monotherapy, as well as other competing treatments that they didn't have included in their clinical trials. The goal was really about quantifying the uncertainty around initial projections for overall survival outcomes. In this case, it was another phase 3 study with first data release of progression-free survival and objective response categorization, omitting overall survival from the first analysis. And those, we constructed a series of projections for overall survival, and we were able to do a retrospective comparison of those methods against the observed data from a later data cut from the phase 3 study. And the goal here was to really evaluate those methods, judge which ones were most accurate, which ones were most appropriate, and keep an eye on the future to try and identify a prioritized list of appropriate methods moving forward for that sort of process of early decision making around uncertain overall survival outcomes. So again, this was a piece of work that was presented at the European ISPOR meeting in 2022. And again, a thank you to the colleagues that we worked with within BMS as well as ICON. But essentially what we sought to do here, and the poster talks about 3 of these methods that we compared, we sought to leverage previous phase data, look at what we knew with a longer observation period, what could we leverage with longer follow-up to give us more reliable estimates of overall survival, and in this case, post-progression survival ended up being a very key category of patients. So one of the methods that we used is a fairly straightforward semi-Markov process model. It's a 3-state model with pre-progression, post-progression, and death as our 3 states. In this case, we sought to construct an overall survival outcome based on the phase 3 data we had on progression-free survival, paired with historic post-progression survival estimates for the monotherapy that was going to be part of this combination regimen. So we knew once patients moved off of their initial treatment, they were going to go on to subsequent treatment. And of course, we made the assumption that their survival performance from that point on was more a function of their subsequent treatment than their initial treatment. But it allowed us to construct a set of overall survival estimates based on that phase 3 PFS for the new product. The second method was a little more simplistic. We looked at some historical data on the sum of, or on the mean post-progression survival time and the mean pre-progression survival time from some historic studies for the monotherapy, compared those times to the PFS estimates of the new phase 3 study, and then made an approximation to adjust the hazard function that was fit to the historic overall survival data in order to construct a projected overall survival curve for the new combination regimen. And then we used another piece for a third method. We used another piece of statistical analysis that was done by the sponsor to look at the surrogacy relationship between progression-free survival and overall survival, essentially looking at the incremental gains in progression-free survival as a proxy for incremental gains in overall survival. So in each case, we constructed a set of survival curves based on the PFS data, and we essentially constructed a 40-year follow-up model to estimate mean survival time, and then calculated the median survival time based on those projections. And then about 6 months or so later from when this work was going on, the second database cut of the phase 3 study was released, and we at that point had access to conduct parametric modeling for the overall survival from that study. And at that point, we prepared this comparison. And what we found was that each of the constructions we developed produced a crude survival estimate that was optimistic. It was above the observed data. But the between treatment difference in our constructed overall survival curves was underestimating what the trial predicted. So you can see from our results table here, we were a bit ahead, a bit optimistic, as I said, in terms of the per treatment survival or per arm survival. But we underestimated, we were a bit too conservative on the delta, the between treatment difference. And then just to illustrate this a little bit further for people who prefer graphs to tables. So on the left-hand side, the trio of graphs summarizes the available data for each of our constructions. So the Kaplan-Meier progression-free survival data and the resulting parametric fit projections. And then the constructed overall survival curves above that. And then you can see in the bottom of the trio, the comparison to the historic overall survival curve for the monotherapy as a benchmark with regard to our forecasting for the combination regimen. And then the right-hand side is a summary of our constructed survival methods compared to the fitted parametric analyses of the revealed overall survival data from the phase 3 study. And again, you can kind of see the difference where we were a bit overly optimistic for the individual treatment results, so the overall survival time per treatment, but we underestimated essentially the distance between the two lines. We underestimated the between treatment difference on overall survival as an outcome. So as I promised, here's a quick list of the publications and presentations that are associated with the material that you've seen here today. In the case study 1, the initial presentation of the method for landmark survival, and then the subsequent publications highlighting the continued evolution of our understanding for that survival data out of the primary phase 3 study from 4 to 5 to 6.5 years of follow-up time. And then in the second case study, our primary graphs and output that were shared for our presentation at the ISPOR meeting, and then a related publication comparing the process of Markov modeling in oncology versus partition survival analysis, just as essentially competing methods for modeling the same process of pre-progression, post-progression, and death as primary classifications for patient health states. So if anybody has any questions on any of these sources or would like to see any more of the material, please feel free to follow up. And with that, Sydney, I think I'm done, and we'll go to questions.
Yes, thanks, Tim. I will actually give you a second here to just catch your breath. If you need a sip of water, go right ahead. And while we are getting ready for our Q&A session, I just would like to launch a link to our survey for the audience. So if you have a moment or need to leave early, you can click here and complete our survey. Let us know what webinar topics you'd like to see in the future. We do keep record of that and keep these in mind. And then you can also just let us know your thoughts on today's experience. So go ahead and click that link if you have to jump off early. Otherwise, it will appear at the end of the webinar as well. In addition, just a reminder of the handouts that are accessible in the Handouts tab. We've got some great resources in there from ICON. And then please continue to submit all of your questions in the Q&A panel. We are going to get started with that in just a moment. So with that, I'm going to bring our speakers, Tim and Manny Kanta, back on. Here we go. Okay, let's get started. So our first question, how does health technology assessments, HTAs, evaluate the proposed approach of incorporating phase 1 data for extrapolating early stage?
Yeah, I think this is one of the questions that we looked at very closely in that first case study. Anytime you do something innovative, it can be a bit of a risk. But I think in general, most of the HTA authorities, I'm thinking specifically of NICE and I guess CDA now, it's not CADIF any longer. But I think their primary focus is to provide a realistic estimate or a best possible estimate of the available evidence. And I think that's really the appeal that we made. We think it's essentially a little short-sighted to set data aside and say, well, no, that's no use to us. It's more relevant, I think, to leverage what's available as best we can to be clear and transparent in how that synthesis is performed. And I think the ESA process, the NICE decision support process, and the ESA, or early scientific advice meetings that are available with CDA, are really powerful in making the case early, presenting the evidence supporting a new or a slightly altered version of a methodology that's been used before, and demonstrating the rationale as to why that's an important advancement or why it's an important element to consider moving forward.
Okay, fantastic. Thanks. Let's move on to another question here. Let's go with, how were those different approaches perceived by the HTA bodies? Are they quite well accepted? And if challenged, what were the main challenges?
I guess I'll speak for myself, and then I'll invite Manikanta to weigh in as well. The landmark example that we talked about, as I said, that was something that we did take through the ESA process. And as I said, I think the emphasis was really on, why do we want to do this? Why are we leveraging this early phase data? What is the opportunity that is lost by waiting until the evolution of the phase 3 trial data is available? And I think in this case, where a patient population is underserved with available treatment options, the case can pretty strongly be made that delaying a decision and waiting for evidence is a bigger risk than incorporating early phase evidence and making best use of the available data. There was definitely some question marks and some uncertainty from the HTA side on how accurate these landmark assessments would be, how optimistic or conservative they may be. But I think we were able to show through a couple of different diagnostic techniques and evaluations in the model that based on the evidence available, we could quantify the uncertainty, and we could demonstrate that the approach was, in fact, a conservative estimate of the overall survival. Manny, I don't know if you have any comments about anything other than the landmark, but I think that's my strongest example of where I've got experience.
I don't have any comments.
Okay. Yeah, in that case, then I guess I'll just refer to some effort from some colleagues on the cure fraction approach. I know that that's something that we've got a publication in the works on, and I'll have to check in with some folks in terms of where that is, what's publicly available. But I think we can maybe have a follow-up in terms of some experience of colleagues on that.
Okay, fantastic. Yeah, thank you so much, Tim. And let's move on to our next question. Based on your insights from case study 2, are there any modifications or alternative strategies you would consider for future analyses?
Yeah, I would say so. I think there are a number of lessons learned. As we said, the goal was to really identify a short list of approaches that would be most relevant in the future. So the goal was to really identify which technique worked, what was the data required, what was the lead time required, what was the uncertainty that came back from it, and how did it inform decision making in the future. I think it did teach us that some of the methods were much easier to construct than others. It certainly taught us that, I think in that slide, it talked about the level of detail that was included in the Markov process model, where we looked at weekly cycles for 40 years, which most people with experience in economic modeling will realize that that's far too detailed for most purposes. But it did give us a couple of working examples that we could rely on and let us narrow down our process so that we could be a little more rapid and a little more responsive to the questions that were being asked. So it did give us some guidance in terms of where to focus. A slightly simpler SMPM would be valuable, or the parametric modeling of prior phase data, I think, is really valuable as something to lean on and include in the analysis.
Excellent. Just in case Manny Kanto wants to add anything, or we can move on.
Please.
I think we're good to move on. Okay. We are getting quite a few questions from the audience, so thank you so much. Keep submitting, please. We have a question here. Do you mind sharing your suggestions and experience on how to leverage knowledge on plausible mechanisms during the survival analysis for immature data?
Manny, I don't know if you want to take a crack at this. I'm just trying to settle on what my working definition of plausible mechanism ought to be.
Actually, so the definition of immature data is completely different from time to time. Actually, immature data come from the limited time of the follow up, and maybe high censoring. So it depends on the where the immaturity is coming from. So the method is going to change totally. So then we can break the observed data into different elements, and we can observe them. So that could be one method. But yeah, where it is coming from, that's really an important statistic to consider.
Yeah, I would definitely agree with that. We really struggled in a couple of those case study situations where we knew kind of what to expect from analogous treatments, but didn't know how much the effect size was going to be expressed as an overall survival outcome. As I talked about, one of those examples really had a key question for a competing therapy with the same mechanism of action. And the expectation that performance would be substantially similar to a competing treatment was valuable in constructing the analysis. But ultimately, through quite a bit of extrapolation testing, we found that trying to tie it to an external source or an external comparison gave us more questions than it actually answered. And we were better off leveraging the internal data in order to narrow down some of those projections. So in some cases, we had to step back from a more aggressive approach just to be a little bit clearer in terms of what we could say and what was still uncertain.
Excellent. Thank you both for your input on that one. Okay, we have another one here. Would you recommend one method over another? In particular, why was the method allowing to reduce the most the uncertainty? I'm not sure if that was clear. I think.
Well, I've certainly got one interpretation of it,
Okay.
but I'll kind of do my best and I'll leave it to Manny. So I think, as Manny suggested in response to the last question, it really depends on your situation. What is the reason that your data are considered immature? Is it censoring? Is it lack of follow-up? Is it questions about patient heterogeneity? Is it something that's unknown about the disease state relative to the treatments? I think the evaluation that he talked about in comparing the hazard plots, looking at the shape of the underlying hazard, considering whether proportional hazards is relevant or if it's violated. I think those are the key questions that go into choosing one of the methods. I do think there is an appetite from the HTA authority to see an approach that begins from standard methods and evolves to reflect what is violated or what is not held. And that allows you to sort of take the analysis as far as the evidence will take you without overstating what's there. But Manny, I'll kind of let you talk about the appropriateness of piecewise and the cure fraction stuff, because I think there are times where that fits and times where it's really harder to defend.
Yes, though there are methods like flexible models, like piecewise models, response-based, everything is there. But the main fundamental is that we always need to start with the basic analysis, and then we need to incorporate the extrapolation, and then we can look into the uncertainty that involves. Then we can combine these models together. That's how we can come to a good extrapolation methods to choose rather than going for the advanced method directly. So we need to start it with the basic analysis. Then after some period, okay, we'll get to know, okay, this is not working out. So that's how it will go away. But yeah, we always need to start with the basic one. Then we need to do the extrapolations, and then we need to see that, okay, where the uncertainty is coming from. Maybe in between we need to discuss it with experts to show how the trend is going on. So yeah, that's how I'll go for a approach over other.
Great. Okay. Thank you very much. We have another question here asking, given the immaturity of data, how do we choose between parametric, semi-parametric, or non-parametric survival models? Are there specific indicators that would guide this decision?
So maybe I'll take this question. Maybe the same answer. So at the starting, we will be looking into the observed data by using the non-parametric method anyway, and then we will be seeing that, okay, are there any covariates that are impacting the survival? So which is again the semi-parametric method, and then we will be checking the proportional hazard assumptions as I mentioned in the slides, and if the hazard plots are parallel and not crossing over the time, then we will be going for uh, independent model, a dependent model with a treatment as an adjustment factor. So that's how we start usually. And if the hazard function is too complex and cannot be understood, then we will be start exploring about the advanced methods. Then only we need to go for that, even though those seems to be too fancy. But even HTA agencies don't want it to go behind that until and unless there is a rationale behind the methodology.
Yeah, I don't really have anything to add. I absolutely agree. It's based on taking it to the level of complexity the data requires to find the appropriate fit.
Yeah, and one more thing is that, so by looking at the clinical trial results in detail, we can see that, okay, let's say, for example, a proportion of patients are responding to the treatment when compared to another segment of the population. So that's where we can see, okay, there might be two subgroups that involved in the population. So then we can start thinking about the response-based modeling, and we can start thinking about there is some heterogeneity that involves. And by looking at the hazard plots, we can see there is a different trend that is observed over the observed period, at the trial period. Then we can break it into the pieces, and luckily if we have very good data, maybe we can break it into several pieces, and we can fit 3 different models. Maybe for first piece you may go for the Kaplan-Meier, you are not going to fit anything additional one. Maybe for other pieces you might be considering standard parametric models. So yeah, that's how it goes on. Thank you. I hope that answers.
Yeah, thank you both so much. That was great. We are close to the end. I want to encourage everybody to keep submitting your questions, though. I will be sending all of these questions to both of our speakers today, and they'll have a look at them, and hopefully we can provide some answers to them. So keep submitting. But I think we have time just for one last question. So let's see here. How would you account for competing risks and repeated events in survival data for immature data?
Yeah, this is actually one of the questions that I just saw as I was scrolling through, and I think it's a really good one. One of the things that we were particularly concerned about in constructing our examples for case study 2 was about the events that defined a PFS observed end. So progression-free survival, you could leave either because you had a progression event, disease progressed, or you had a fatality event, patient died. So understanding the difference between those two and incorporating a different consequence in our constructed model was really key in making our appropriate assessment for post-progression survival something that would be adapted to the phase 3 data. So a couple of different ways that you can do that. One of the other things that we consider a lot in the partition survival analysis is duration of therapy, which is a clinical event in a certain sense, but it doesn't necessarily change the patient's status. Discontinuing from some treatments just means you've reached the end of your prescribed course, not that you've had disease progression, not that you've died, not that you've had a worsening or an improvement. So in that case, we're able to construct treatment duration as a excluded event from the partition survival model. We consider it essentially on a different layer. And there is the opportunity to do that, to construct your time to event analysis based strictly on the layers that directly compete. So death and progression would be directly competing for the end of PFS. And that PFS can be constructed with only those 2 events included in the data set. It gets much more complicated when you have multiple competing events, and you'd be looking beyond a simple time to event analysis. It's really a different discussion for maybe a different set of examples, and I think we can talk through that with some different follow-up. But I think we're happy to provide a couple of examples, either from the literature or from prior experience on competing time to event models, particularly things like the UKPDS. It's a set of risk prediction equations developed in diabetic patients in the UK, and it includes multiple outcome predictions based on a set of competing event structures. So I think there's some good examples there that we would point you to, and we can follow up on that.
In closing, we hope you enjoyed this HealthEconomics.com webinar sponsored by ICON, and I hope you enjoy the rest of your day.